Okay, in this talk I'm going to give an overview of the accelerator systems for Tesla and the NLC, which is a lot like the JLC. I'll also give you an update of the R&D status for these programs and talk a little about the CERN CLIC project as well. So why are we interested in beam power? Well, as you can imagine, the beam power is related to the luminosity that you can get from these machines. In fact, as an approximation, you can write that the luminosity basically scales as a beam power divided by normalized emittance of the beams. This is the vertical phase space of the beams. So the goal then of the accelerator system is to deliver as much beam power without degrading the beam emittance. And in the next talk, you'll hear much more about the luminosity or the emittance preservation. And in this talk, I'm going to tell you about basically maximizing the beam power. So you can write that the beam power, in fact, is just basically the wall plug power times the efficiency of the machine to deliver AC to the beam. And in practical terms, the wall plug power is limited to a few hundred megawatts from cooling operation cost issues. And then the efficiency is a function then of the technology, and I'll go through that in some detail. And also how you divide up the beam in terms of the number of bunches in the bunch train is also a function of the technology, as you'll see, and it's quite different for these two approaches. So if you're in the market for a linear collider, and you start thinking about what it is that you want to build something efficient, the general approaches are using normal conducting copper accelerator structures, as has been done at SLAC. Here you want to go to high frequency to be efficient. This allows you to maintain this efficiency with a lower energy per pulse, making less components, and also at a higher gradient, so your LINAC is shorter. And the NLC, JLC have chosen 11.4 gigahertz. And of course, I forgot to mention the downside. There's a downside of this, is that as the beams go through the structure, they generate wake fields, which act to degrade the beam emittances. And so that's a trade-off that you have to deal with here. And at 11.4 gigahertz, I think that's manageable. And here the optimal gradient is about 70 MeV per meter for this choice of technology. CLIC is a little more aggressive. They're aiming for a higher energy, a 3 TeV. They've chosen 30 gigahertz and are aiming for 170 MeV in their LINAC. The other approach you could take is using the superconducting technology. Here basically you're exploiting the fact that at superconducting temperatures, the cavity losses are low, and this allows you to efficiently deliver energy to the beam slowly as well, where by slowly I mean using a low current beam. And this means that you can use less expensive low peak power sources. However, it means that the damping range are going to have to be very big. Your bunch train is going to be very long, and that's a drawback on this approach. And Tesla has chosen a lower frequency, 1.3 gigahertz. These arguments still apply. It's just that there's a term related to the surface resistance that goes up as a square of the frequency that keeps them at lower frequencies. Their gradient of 23 is based on their initial site layout, which was, of course, related to an initial estimate of what they could achieve as far as the superconducting gradients. Is quite a challenge to get up from the about 5 MeV gradients that were available 10 years ago. And that's, however, their cost optimum is higher. If they had a choice, they would certainly like to go to higher gradients for both expandability and for cost minimization. So let's go through what some of these structures look like in each case. This is the NLC, what we call the rounded damp detune structure. A lot of acronyms in this game. Anyway, the damping detuning refer to the fact that the way the long-range wake fields are suppressed, and we won't go into that much today. Mainly, the idea here is that you have, in this case, 2 meters of accelerator structure. There's 206 of these cells. And sort of the time scale related to X-band is this 100 nanoseconds. That's the attenuation time in a structure like this, and it sets a scale for a number of things. And you make these so that the fill time is roughly the attenuation time. These are operated at room temperature, actually above room temperature, and the losses are about 3 kilowatts a meter, so it has to be cooled. And in steady state, about 50% of the 170 megawatts that go into this to produce 70 MeV goes into the beam. So about half of the power goes into the beam, and then of course you have to fill the structure up front. In Tesla, they're also using cavities that are, in this case, about a meter long. They have 9 cells. Everything's bigger here. They're using a lower frequency. The diameter is about 70 millimeters compared to the 10 in the NLC. This is made out of pure niobium. Like I say, they're sort of limited to the number of cells and the length you can do it with a standing wave type structure. They run in about 2K in superfluid helium. They're very sensitive to surface resistance. It goes up very quickly with temperature. This means they have to keep the things very pure, and the main thrust of a lot of their R&D program is to remove any contaminants or inclusions in the niobium. Their Qs are very large, 10 to the 10th, where their losses are only about a watt a meter. That's very low. On the other hand, it takes about a kilowatt a meter to remove a watt a meter. In fact, this limits them from going up to sort of CW for running this thing. So there's what you gain on one end, you lose on the other. However, they adjust these cavities. They tune them such that the external Q of these things match the beam. And that's effectively a Q around 10 to the 6th, and that's, of course, much smaller than the 10 to the 10th, which means in steady state, essentially 100% of the RF instead of 50 now go right into the beam. So you can't get much more efficient than that. And they only take 230 kilowatts instead of this 200 megawatts, so it's very low power, and everything's, like I say, on a long time scale. In fact, here the relevant scale is 420 microseconds is the fill time of these cavities. And so generally, in both machines, you make the bunch train length. You want to make it longer than this value to be efficient, but you don't want to make it too long, otherwise you're producing a lot of energy that you could make up for by just increasing the rep rate. And so both in the Tesla and NLC, we run bunch trains that are roughly about 2.25 times longer than the fill time, and that basically sets the scale of the beam parameters. So let's look at some of the efficiencies associated with this. Is sort of a bottom line plot for how you transfer energy from the wall plug, you can think, to the beam. And what I'm showing here is the general layout of a fairly simplified RF system, where you start by generating a high voltage pulse that drives the klystrons. There are big RF amplifiers. This RF power, at least in the case of the NLC, needs to be compressed. It's more optimal in the NLC to produce long pulses that get compressed down to shorter ones. And then this power goes into the accelerator structures to drive the beam. And there's associated efficiencies all throughout this system. And one of the biggest differences in accelerators is basically what I've told you, that roughly a factor of 2 difference here relating to this steady state loss. There's a filling time loss, there's overheads, but roughly a factor of 2 difference because they're using superconducting technology. The others are similar. These are the NLC versus Tesla numbers throughout the system, which means that the overall NLC takes about 10% of the wall plug power goes into the beam, and Tesla's more like 24. There's associated cooling cost. Adding all that in, you get about 100 to 140 megawatts of power out of the wall. And this is for just for the 500 JEV case. Now, of course, these machines are a little more complicated than I've shown you here, and there's all sorts of tricks you can do to try to make them more efficient. And that's certainly what we've been concentrating on. Instead of just running one klystron that runs one structure, as I've shown, we actually gang 8 structures together running off of one modulator. And this power then is basically summed and sent up beam. The beam comes in this direction and slices, and each slice then matches the beam here. And there's this multi-moded system where you encode the power in different pipes and different modes to efficiently send it up beam here. You're trying to minimize the amount of plumbing effectively to do this. And in the NLC, the tunnel, it would look something like this, where These pipes that carry the RF would be up on the walls here, and these would be the accelerator structures on the on girders that are movable, and each would have its own feed. In the case of Tesla, they, as I mentioned, they have a lot lower peak power. In fact, the klystrons are aiming for about 10 megawatts, and that's enough actually to drive 36 of these 9-cell cavities, and they're actually grouped into 3 sets of 12, where each set of 12 is in what they call a cryo module that has all the superfluid helium in it. And each individually fed through with a tuner, phase tuner, and an isolator, and something to adjust this external Q to match the beam impedance. In the future, they're going to what they call a superstructure, which is basically just 2 of these cavities together with just 1 input. This makes it a little shorter so they can put more cavities into here. And their tunnel looks something like this, where these are these big cryo modules with the accelerators inside. They also put their klystrons and the transformers from their modulators in the tunnel itself, and the primary to the modulators is actually sent out on these high voltage cables, about 10 kilovolt pulses. Their tunnel also serves as their part for their damping ring. Their damping ring is sort of a dog bone shape, and you'll hear about that in the next talk. It's about 18 kilometers in circumference, which is almost the length of the Linac. Now, just to step back a minute, talk a little about CLIC. It's sort of interesting, and that it's in some ways it's a hybrid between the NLC and Tesla. It uses some of the features of each. And here they're aiming for a higher energy in the future. And basically, instead of directly generating RF and going right to the structures, they generate what's called dry beam. They put the energy in a beam first. And they do this sort of like Tesla in the sense that they use lower frequencies and a very long pulse of current. And then they compress the pulse so that it's very high current now. And this current then runs through what they call transfer structures. You can think of them just decelerators that generate the RF. And then the RF only has to go through about a meter to accelerate the beam. But it's very high peak power, and this is all done at 30 gigahertz at this end. And the big selling point here is it's really expandability. Their efficiency is not that much different than the NLC. It's just if you're going to go to very high energies, this part of it would not have to change much. It's just the pulse lengths would get longer, and then this would just be lengthened. So again, the selling point's more in the expandability at higher energies. The efficiency is not that much better. Let's go through now some of the parts for the components of the NLC and Tesla, and tell you a little about where we're at on these. The klystrons generating around 50 to 75 megawatts. We have for the test accelerator a number of what we call solenoidal focus tubes. They produce 50 megawatts. We have 10 of them we use for testing all sorts of structures and running beam. However, they have these large solenoidal magnets to focus the beam here from the gun up to the collector, where this is the RF output cavity. It's basically modulated, basically vacuum tube amplifier, you can think of it. And this takes a lot of power, about 25 kilowatts, which would really kill our efficiencies if we kept doing that. So we've gone to these periodic permanent magnet focus, basically using permanent magnets to focus the beam throughout here. And we had success building these at 50 megawatts, and they're working more now on the 75, a little more of a challenge. The first one, after some fixes, we got to basically performance specs that we were desiring. And right now we're just about to test this next version here. A diode version of this without any RF cavities has been run, and it's produced 3 microsecond pulses at the 500 kilovolts. And like I say, we're just starting the RF testing of this. We'll build more next year. One of them is going to be with industry, and we'll build a number of them for the system test I'll talk about a little later. In the longer term, there's what they call sheet beam klystron. It's a version of this that will hopefully lower the cost. It has a lower space charge in it. Also, in parallel, at KEK, there's a program to develop these type of tubes. They're working with Toshiba and they've built a number of these already. This is called PPM2. It's a 75 megawatt tube. In their design, they're only looking at 1.5 microsecond pulses instead of 3. It makes it a little easier. It's not clear what the real limitation on these. Most of our testing has so far been limited by the modulator and not by the klystron itself. But basically, they've gotten close to the specs that they were aiming for. And again, likewise, they're going to build some more of these with Toshiba in the next year to improve efficiency and make it easier to manufacture. In the case of Tesla, they're also working with industry. They wanted a 10 megawatt tube. And to improve efficiency, they've gone to what they call a multi-beam klystron. Instead of a single beam that goes through here, you split the beam up into 7 beamlets. You can think the reason for doing that is that the space charge forces are smaller because the current's smaller. You only have about 20 amps at 110 kilovolts in these cases. And this brings up the efficiency quite a bit. They're aiming for 70. They basically achieved 65. They built 3 of these tubes. One of them has been used in their test facility, which is called TTF for the Tesla test facility. And they're just about to test, I think, their 3rd one now. And so these are, of course, longer pulse klystrons. Now, these klystrons require a power source, and in some cases, the power source can be as expensive as the klystrons. And at SLAC, in combination with Livermore and Bechtel, Nevada, we're developing a solid-state modulator instead of the Thyratron-based ones that have been used at SLAC in the past. And it's a fairly simple idea. The idea is just to charge up a capacitor and use these what they call IGBTs, which are insulated gate bipolar transistors. They're basically super transistors that have been developed for the train industry. They're very fast, surprisingly, given that trains don't need to have 100 nanosecond switching time. But it turns out they, unless it's a very fast train, it turns out they can switch megawatts of power very efficiently. And basically, we turn these on and run a primary loop here, and then using these met glass cores as a transformer, sum up the voltages with stacks of these. So each one's about 2 kilovolts. You stack them up. And this is just a test setup for this. And the goal for the NLC is to put 76 of these cores together to generate these 500 kilovolt pulses that we'll need for the NLC, and this will produce a gigawatt of pulse power. This will certainly start your car on a cold morning. And so here's the 8 klystrons and the 3 cores, and they use a 3-turn secondary here to get the voltage up. And we've actually built one of these. I'm just in the process of testing it. This shows these stacks here with the driver cards on them. We don't have the X-band klystrons right now, so we're using S-band ones as you can think of diode loads. We also use what we call a water load. This is the close-up of the 3-turn secondary here. Of course, you're holding off 500 kilovolts here, and this is all actually done in oil. This is all filled with oil afterwards. And so that basically works. This just shows a pulse here where it was run into a water load with 500 kilovolts at 600 amps. And then when the full testing will be at 2,000 amps when this runs. So this is quite an innovation. Tesla also, they've been reasonably innovative as far as their modulator. It's based on a design developed at Fermilab. Has what they call a bouncer circuit. And again, these are fairly simple circuits in the sense that you charge a capacitor and you turn on a switch and you discharge it. Now, when you discharge a capacitor, you have a droop to it. In this case, it would be about 19%. And they have what they call a bouncer circuit, which is basically charged up in advance and discharged at the same time, so that the droop in this circuit discharge at about the same rate, and it gives you a flat pulse at this end. And so they're working, they started with this design, they're working with industry to make improvements and to use that for their machine. So let's skip here. So let's talk about now the gradient considerations for both of these machines. It's been a challenge in each case. Some of the considerations for the NLC, as I mentioned earlier, the cost optimal gradient for the NLC is about 70. However, that's fairly flat, and you could probably go 15 MeV either side of that and only change the total project cost by less than 10%. But anyway, we're aiming for for 70. And in fact, for both the 500 and our 1T EV designs, it's based on 70. Where in the case of the 1T, initially we'll build just basically half the LINAC, the other half will be a drift section. And so that's what we're aiming for both of these designs. However, in the future, if it turns out for that second half of the LINAC that if the power sources get cheaper, you may want to run at even a higher gradient, so you want to be able to hopefully show that your structures will run at even higher gradients in the future. And in the past, we've done actually better than 100 MeV per meter. This was done at a time when we didn't have very high power sources, and so we used standing wave structures and low group velocity structures. You can think of the group velocity just related to the inverse of the amount of power you need to achieve a certain gradient, and so it did well in the past. However, when we optimize these structures for cost and efficiency, we ended up with a much longer structure, about 2 meters, and a higher group velocity. The group velocity is the speed at which the RF pulse propagates through the structure. And it's related, the integral went over this, is just the fill time of the structure. And they start at 12% and go down to 3%. And when we ran them up to around 50 MeV, we found they processed very hard, and when we took them apart, we see that the irises were fairly heavily pitted, but mainly just at the front end. It sort of looks like craters of the moon on here. But the back end, there's sort of a purple haze on this thing from oxidation, but otherwise it's not very pitted. And so we believe there's something related to the damage that's related to the group velocity, and that at lower group velocity you have less power, and then the impedance of the system is much higher. And so we have a fairly aggressive program to address this sort of problem, and we've made quite a bit of success. The main part of this program is to compare different types of structures with different parameters, and ones with lower group velocity. I mean, basically, you saw the structure the back end of it works, so why not make the structures look like the back end? And that's essentially what we're doing in this part of the program. We're also looking at different ways of cleaning them and producing them, whether diamond turning or polydiamond turning makes a difference. And we're also running standing wave type of structures as opposed to traveling. And thus far we've processed 12 structures with over 5,000 hours, and I'll show you some of the highlights of that. And then in parallel, there's a systematic study of breakdown. Surprisingly, after so many years of RF work, that the sort of fundamentals of why things break down and the sources of that are not very well understood. And also, we're a program of just improving the way we handle these structures, a lot like what Tesla has done to improve their performance. And so just as a highlight, for these traveling wave structures, the best results we've gotten with the ones with 3% initial group velocity at the front end, and at the back it's about 1.5. And in one case here, we run up to 86 MeV per meter, and then we drop. Usually you go up like anything when you process any high voltage system, and then drop back. When you drop back to 70, you get only about 1 breakdown in 200,000 pulses. Now that sounds very, very small, but it turns out you really want more like 2 million, so that the amount of trips in the NLC where you have 10,000 of these structures is fairly small. And fortunately, we think that at that level, most of these trips are occurring just at these input and output couplers, and we have solutions that we think that will improve that. But even if you didn't do that, if you drop down to 65, you get down to levels that are acceptable for the NLC. Also, this damage level, the amount of phase advance that occurs when you start to chew off the irises is an acceptable value. And so in the next year, we're going to test more of these at 3 and 5%, and make versions that are more acceptable for the NLC in terms of having this weight field control on it and having the iris size that are acceptable from that point of view. Another success has been with the standing wave structures. Here you basically fill the structures just from the center. Instead of a traveling wave going through it, they basically just fill up uniformly. And one advantage of this is that you only have to run at the loaded gradient in the NLC, which is 55, not the 70. So this lowers down the field requirements. And in a recent test, these are fairly short. They're about 20 centimeters long here. The one that ran with less than 1 in 8 million pulses. So basically it stays on all the time. and didn't see any damage. So these are certainly a candidate for the NLC. And in the next round, we even have ones that will have a smaller surface field for the same acceleration gradient. And the more of a challenge here is incorporate this wake field control, damping out these long-range wake fields that are generated when the beams go through. Yeah. Okay, in the case of Tesla, they also had quite a success over the last decade. In fact, the challenge here was, over the past decade, was to, like I say, increase the gradients that had been achieved at, for instance, at Cornell, which were down at only at 5 MeV level, up to around 25 to make it a linear collider even be conceivable. And also they needed to try to reduce the cavity cost as sort of a comparable factor. And they basically on the experience from the initial industrial fabrication at the cavities for CBAF. And they did, of course, a lot of improvements, especially with the material QC and various techniques to you can think pre-process the structures before you turn on the RF. For instance, sort of the heat treatment, there's ultra-pure high-pressure rinsing and high-power processing, and I'll show you in a minute. And basically, they've claimed to achieve their gradient goal of around 25 MeV per meter. However, their emphasis now is to be able to increase this up to 35 so that they can upgrade to 800 JeV in the center of mass. So this is turning out more the focus of their program now. So for these cavities, one of the things that challenges they face is the field emission. It's not so much breakdown that you get this cataclysmic event where you get a big current pulse, but you get these fairly small current pulses due to, for instance, particulate matter on this residue on the cavity. And because there's such a high Q system, it doesn't take much current to load down the RF in the structures. That's one of the disadvantages of having a high Q system. And this just shows a diagram of what some of the current would look like. And they actually, because they can use temperature sensors to locate these emitters by looking at the heat from the current that's emitted from these things. And they can actually isolate individual emitters on these things. So the way they generally characterize their cavities is by these Q versus gradient curves. And this is a series of curves for their latest production of cavities, which show the Q, again, at the 10 to the 10th level versus gradient. And as you can see, as you get to higher gradients, you get an exponentiation of this current, which then loads down the Q of the system. And because the cooling system is limited sort of at the 10 to the 10th level, this is watt per meter, which again sounds very small, but very hard to remove that. They want to keep above this line, and of course their gradient goal is 23.4 here, and so they want all their curves to be above that. And you can see they've done very well on that. And then the bottom part just shows some of the this gradient as a function of their production series. They started with the original TTF about 5 or 7 years ago, and they've improved since then. Sort of the bottom line performance, though, is they put 8 of these in this cryo module, and they run it with beam, and these are the red dots here. And so their latest cryo module is getting very close to their design gradient here of 23. They're sort of, when you put them 8 together, sort of limited by the weakest one. If it doesn't work, you have to lower the rest of them down here, so they're a little more limited in that sense. Now, as I said, the goal is to increase the and one of the ways that they're looking, I think, really relying on is this method called electropolishing that was developed at KEK. And basically, as part of their preparation, they use these acid baths to etch off sort of 100 microns of niobium. And this is sort of an etching process, but it's done under current flow as well. And this leaves a much smoother surface than their normal, what's called buffered chemical polishing. And it seems to allow for higher gradients. And in fact, for single cells, instead of the 9, you just have a single cavity. They've been getting up to these levels of up to 35. And in their higher energy design, they're going to allow Qs down to 5, 10 to the 9. So these would basically meet that. But again, they're only single cavities, and right now they're in the process of doing this for these full-scale cavities, and they haven't quite got there yet. But again, it's sort of early in the development stage of this. And just a brief mention of what CLIC is up to. They've been working on their structure designs, mainly in terms of damping and detuning this control of wake fields. They've done some reasonable designs, although they still have some drawbacks. For their high gradient work, right now they're limited by a power source at 30 gigahertz. And right now they use this smaller two-beam system, but it only gives them 16 nanosecond pulses where they need 130. However, even some of their test structures, they're starting to see resistance at the 60, 70 MeV per meter. So they have a way to go to get up to the 170 that they're aiming for. And so this will be a big program in the future. Let me go on now to just mention a few things about the system test of this thing. I've shown you all the cavities and the modulators and the klystrons. And if they're going to work for a linear collider, they all have to work together and work efficiently. And for the NLC, we have the NLC-TA, which is the NLC Test Accelerator, where we've been doing this type of work. And it was built originally what we call first-generation components that have this sled pulse compression system. But it has allowed us to really debug a lot of these components and serves as a test bed now for the components we're developing. And one of the next steps will be we have this what we call an 8-pack project, which I've shown you earlier. There's 8 klystrons that will drive an RF system. A simpler version of that will be tested at first, where we just have 2 klystrons, and we'll run what we call sled pulse compression system. I didn't have the time to go much into the RF transport today, but by the end of this year, we're going to be running this system, which will generate the sort of pulses, peak power, and lengths that will be required for the NLC. It won't be the final NLC version, but it will show that these type of components that are needed for the bigger system will work. And like I say, it serves as a test bed. And if need be, this sort of a simpler system could be used as an alternative for the NLC if it deemed necessary. And then the bigger test will come a little later. This will be done in stages, but the full-scale version of this will be in mid-2004. And it'll basically is integrated test the essential components that I've shown you, everything that you would need to really build all these RF units for the NLC. It has this induction modulator, actually a second-generation version. The first one will be used in this previous test. It has the 8 klystrons, the essential elements of this delay line system, and basically 11 meters of structure. At Tesla, they have what they call the TTF, and it's part of a facility, a user facility that generates, where they do FEL research and generate light for users. They basically have 2 stations here where they have 2 of these 8-cavity cryo modules, where the results from the test I showed earlier, where they're able to get up to around 22 MeV per meter. So these are these 8 cavities here that are used inside here. And this is a picture of what the LINACs look like. And this has been around for over 5 years. And they're upgrading that to, again, to be more like look like what the Tesla LINAC will look like. It will, again, be a user facility where they'll generate a 1 GeV beam to generate certain nanometer level wavelength X-rays. And for the 1 GeV, it will require about 50 meters of accelerator of 6 cryo modules with the 8 cavities apiece on it. So this will be quite an accelerator. One of them will have these 8 electropolished cavities where they're aiming, again, for this higher gradient of 35 MeV that they need for their 800 GeV design. And the testing, the high gradient part of this testing will begin in 2003, mid-2003. So just a brief recap then of these energy upgrades, since that's a major part of the program in the next few years. As I mentioned, for 1 TeV NLC, you basically fill the second half of the LINAC with the RF components, the same types that you developed for the first half. And you run with basically the same beam parameters, and it takes about twice the LINAC AC power, another 100-some megawatts to get up to there. And Tesla, they keep the actual, again, they keep the beam line the same, the cavities the same. They're aiming for having these cavities work at 35 to begin with. It will require doubling roughly their cooling capacity and also the number of klystrons and modulators, and their AC power would increase by 50%. They also lower the rep rate down some. And just a general mention of Click, that again, their selling point here is their expandability. They would basically just lengthen the linac and increase the length of their dry beam, which of course require higher modulator and klystron capability. Okay, so to conclude, if 500 GeV is your terminal energy for these machines, then with either X-band or the superconducting technologies that's been demonstrated over the past 5 years, you could build one of these basically using, for instance, these Tesla Clio modules, which already run at 23, and a lot of the X-band power source things that we've developed for the NLCTA and have been working on. However, for the main targeting for the next few years, as I mentioned, is to improvements to secure 800 to 1,000 GeV center of mass. And this will need the Tesla Cryo modules with 35 MeV and this 8-pack type of power source and distribution system that I showed you. Like I say, Click is a little behind here. They need to develop a power source to even do their testing. Their CTF facility, which is a two-beam facility to start to test their two-beam drive system and will allow them to do gradient studies, will begin in 2005. And finally, I think as mentioned earlier, there's a design, or a comparison being generated of the different designs. That will be a first step for doing a real technical comparison of these machines. So thank you.